Hey guys, so it's been a while since we had a video, so I thought I would make one for you and let you watch it. This should not be a very long video because this covers the concept of ions, which we have already been doing for quite some time. Really what I'm explaining today is using Aufbau's principle. Why do specific elements have, specific atoms have the configurations they do have, and why exactly do elements want to be like the noble gases? So you know that elements want to act like noble gases, and so now today we're going to learn about why they want to do that, and then we're going to learn a little bit more about the transition elements. Again, a lot of this is a review, so I don't have a lot of notes on this. I am going to be talking quite a bit though, so hopefully you're listening to this right now, because I will probably tell you to add some things. I will add some things in class as well. I don't expect like I said, I don't expect these notes to be super long, but you should leave a little bit of space because we will get into more details and I'll give you a lot more examples than I have traditionally in the past. So after this video, you should be able to determine the number of valence electrons for any element and draw an electron diagram for any atom. Use the octet rule to predict the charges of the most common ions formed by the representative elements. Write electron configuration for ions. Identify other atoms or ions that are isoelectronic with a particular ion. And finally, know the transition metal ions with either half-filled or completely filled d sublevels are particularly stable. So there's quite a few things there. Like I said, most of this should feel like a review, not just from this class, but from Science 1 as well. I'm informed that you guys have done Lewis dot structures and all of this, so I don't expect this particular video to be crazy. So in the past, we have talked about some crazy things, and this all relates to the idea of ions and ionic compounds. And these are not the only type of bonds that exist. There are different types of bonds, but a huge type of bond is known as ionic bonding. And that plays a huge role in the fact that valence electrons come into play, and they are transferring electrons from one to the other. Now, at this point, you should probably know that valence electrons are transferred from metals to nonmetals. And this is all based off of ionization energy, affinity, Aufbau's principle, and all of these things are things that should not be brand new to you. So a couple things to remember. Remember, ions are formed when atoms lose or gain electrons. Metal atoms have relatively few valence electrons, so when their neutral metals undergo chemical reactions, they tend to lose in comparison to nonmetals that have more valence electrons, so they tend to gain. That's not the only reason why they lose and gain, but that is another big reason. It's easier to lose one of something instead of trying to get the energy to gain 7. For example, you probably are more likely or really want to lose 1 pound in comparison to gaining 7. All right, so let's go ahead and just get into the details and how we represent ions a lot of times, or just any regular atom, is by an electron dot diagram. And this is something you should have seen. So a couple reminders, valence electrons can be easily determined from electron configuration. So remember, the configuration looks something like this: 1s2, 2s1. And if you look at that element, you count these numbers up. Oops, my pen is not working. But if you count 2 and 1, you get 3. That's 3 total electrons. That tells you that we're dealing with lithium. And if you look at the very last number in the s orbital, this is the number of valence electrons. So if you add the 2 subscripts up, you get the total number of electrons. You add the last number, you get the number of valence electrons. Again, this should all just be a review. Another reminder for elements in the S and P blocks, these are also known as the representative elements. The number of valence electrons can be easily determined from the group number. So groups 1, 2, 13, 14, 15, 16, 17, and 18, those are the representative elements. We can determine those by looking at the very last number. So groups 1, 2, and 13, they have 1, 2, and 3 valence electrons. Groups 14 have 4, 15, 5, 16, 6, 17, 7, and finally 18 with 8. When dealing with chemical bonding, which is the big thing we want to do, right? Atoms, believe it or not, do not want to stay in a neutral state. It's so much easier for them to give away or take electrons so that they are in a more stable condition than to be by themselves. Typically on the periodic table, you're not going to see very many nonmetals, and even some metals found in nature by themselves. They're going to be bonded to something, and so a lot of times we're dealing with ionic bonding. Whenever you create an ion, there is a capability of creating a bond with something. So in dealing with chemical bonding, keeping track of valence electrons for each atom is super essential. So that's why we're going over this again. It's very important that you know how many valence electrons atoms have, especially from groups. So once you get the pattern of the group number equals the valence electron number, this will really help when you see the bonds, because eventually I'm going to come to a time where I'm going to say, is it possible to create a bond between lithium and fluorine? And you need to tell me yes or no, and why or why not. And a great way to represent valence electrons is by making an electron dot diagram. And so this shows the valence electrons of an atom as dots distributed around the element symbol. So like I said, you want to keep track of your valence electrons. A great way to do this, electron dot diagram. And so right here we have the configuration for lithium. I'm going to show you the electron dot diagram for that. And when we do the electron dot diagrams, you only include the valence electrons. So lithium is a group 1 element. That means it only has one valence electron. So you're going to write the symbol for lithium, and then it's going to have a dot. I am not super particular on where you put that one dot. So if you want to put it up here or down here or starting there, that's up to you. The big rule, though, when you're dealing with electron dot diagrams is to distribute the electron around the symbol first. So the reason for this is because electrons have the same charge. They are negatives. So any kind of charge that is the same, they repel each other. So that's how it's represented on the electron dot diagram, is that you distribute them around. And so what I mean by this is, let's look at a different element. Let's look at beryllium. It's in group 2. So that means it has 2 valence electrons. So Be. Instead of putting the dots like this, that's a no. Because those electrons repel each other, you want to put the dots and you want to distribute them around. So you're just going to go around. Like I said, I am not particular on how you go around them. You may take college classes and they may be particular on that, but I am not. As long as you can demonstrate and illustrate that there are 2 valence electrons around that particular atom, I'm not going to dock you for that. All right, so that last slide, I know I talked a lot, but there is a lot of information in there, probably a lot of recall. You just got back from a break, so you're probably were not thinking about ionic bonds at all, and that's all right. So just a little brief reminder. Now we're going to start talking about some things, and you probably already know some of this, but we're not going to just put a little bit more background to it. There is a fancy schmancy rule known as the octet rule, and if you've ever seen the prefix oct, that stands for 8, so you should know we're dealing with 8 here. There's this fancy chemist by the name of Gilbert Lewis, and he used the idea of unreactive noble gases to explain the types of ions and molecules that are formed by other elements. So basically what he did was he looked at the noble gases and he was like, hey, you're not reactive. And he created this rule based off this, and he formed this idea on why atoms bond the way they do with other atoms. And so what he said was he created this octet rule, and it states that elements tend to form compounds in ways that give each atom 8 valence electrons. Now, there is an exception to this rule, and you should probably already know this exception. The exception to this rule is that elements in the first period, which are particularly stable when they have 2 valence electrons. Remember, in the first period, we only have hydrogen and helium. Helium has a max number of 2 electrons. And I showed you those valence shells. And remember that s orbital can only hold 2 valence electrons, or 2 electrons in general. So the more generalized rule on this, and I actually like this rule better than what's stated for the octet rule, so I would highlight this second part, is atoms react in order to achieve the same valence electron configuration as that of a noble gas. Now there are a couple ways that atoms can satisfy the octet rule. One of those ways is that they can share valence electrons with other atoms. Sharing is great. This is known as covalent bonding. We are not talking about sharing today. We are talking about taking and giving, and only the strong survive. And so we're going to be focusing on ionic bonding for this chapter. The next chapter, we're talking about sharing. I don't find sharing as fun as I do ionic bonding. I think that's where the best reactions are. Again, remember, we are only dealing with valence electrons. So whenever we are taking or giving away. We are only talking about valence electrons. Again, we're back to some review, cations versus anions. So what is a cation? A cation is a positive ion formed when an atom loses one or more electrons. And so remember a couple of things about cations. They are typically metals. They're most commonly formed by the representative elements, and those are that involve the loss of all valence electrons. So your alkali metals, your alkali earth metals, and group 13s, those are the typical elements that are going to lose, and meaning they're going to have more protons than electrons. That's a really big important fact, you guys. Some of you really struggled on that part of your test, so we need to make sure that we cover that and we really get that down, because when it comes time to making reactions, it's going to be pretty important. So let's look at another example. Let's look at sodium. Sodium has a total number of electrons that it has is 11, but it is in group 1, so that means it only has one valence electron, meaning it only has one to lose to a different element, whichever it wants to bond with. In order for sodium to have a complete octet, or to follow the octet rule, it wants to lose that electron in order to look like neon, which is the noble gas that's above sodium. So remember that noble gas configuration, atoms want to look like they're noble gases. When sodium loses that one electron, it now looks the same, or it now is similar to the noble gas neon. And so there's a term that describes this, and it's called isoelectronic. And this is used to describe two atoms or ions that have the same electron configuration. Remember, sodium has just lost that one valence electron, and so it now looks like this as its symbol. That plus sign indicates, oh, I lost that one electron, but now the configuration is the same as neon. Now, don't get this confused. I'm not saying that sodium and neon are the exact same atom, because we're not losing protons. We're not gaining protons. You cannot do that. We are only losing and gaining electrons. But when you lose or gain an electron and those look similar to a noble gas, they become isoelectronic. Now, there are other different atoms that can be isoelectronic to sodium and to neon. Others would be like magnesium or aluminum. Magnesium losing 2, and it looks similar to neon, so that means it's also going to look similar to that sodium ion, or that sodium cation. The same with aluminum. It loses 3 electrons, so it's going to have the same configuration as magnesium, sodium, and neon. Like I said, that doesn't make them the exact same atom. It's just telling us that we have the same number of electrons, and that is a stable state for those atoms. Second part, remember anions, and these are the negative ions formed by gaining one or more electrons. I still think that sounds weird. When non-metal atoms gain electrons, they often do so until they reach an octet of valence electrons and their outermost principal energy level. Again, we are trying to reach a number of 8. We are typically going to deal with groups 15, 16, and 17. Group 14 we'll talk about a little bit, and when we talk about organic chemistry, and we are going to spend quite a bit of time, I shouldn't say quite a bit of time, organic chemistry is very depressing. But we will talk about organic chemistry and carbon and why it is so significant in life. But right now we're going to focus on groups 15, 16, and 17. And all I'm saying is that these typically gain electrons. It's so much easier to gain 3, 2, or 1 electron than it is to lose all 5, 6, or 7. Final thing I want to talk about is transition metals and their ions and what they create. Transition metals are funky because you can have, like iron, for example, can lose 2 or 3 electrons depending on what it wants to bond with. They're really just kind of funky in that way. Typically, most of your transition metals are going to lose 2 electrons. And so the reason for this is due to Aufbau's principle and also the filling order. So remember, if you don't remember Aufbau's principle, remember that electrons fill in a particular order, and electrons in the 4s sublevel, because they don't have as much energy as that D sublevel, they fill before your 3Ds. However, when it comes time to get electrons or pull electrons from an atom, they're going to pull from the s sublevel. It all has to do with that energy again. It takes less energy to give and take from the s orbital than it ever will for the d, the p, or the f. And that's why typically transition metals, it's hard for them to lose enough electrons to get that noble gas configuration. Like I said, a charge of 2+ is common for transition metals. I'm really not going to go into more detail than that. I'm just going to focus on the representative elements. Transition elements, you really should just know, because of the fact that they have that d sublevel, it's very difficult to take and gain enough electrons to get to that octet rule. Another thing is that it's kind of weird, but transition metals, even when they're half filled or they're completely filled in that d sublevel, this still gives them that stability or that groundness that they prefer rather than being crazy and unstable. If you have any questions, please ask me on Edpuzzle. I realize that this video went longer, and I know I said it wasn't supposed to go long. Kind of got crazy, so sorry, but not really. Ask me questions on Edpuzzle.